This is example 2 from lecture 4, part 1. Okay, so this problem says, first of all, note that it doesn't involve graphical integration, but instead analytical integration. This is just a note because this section is on graphical integration, understanding acceleration, velocity, and position, and the relationship between them as the area under the curves. However, it's just as useful to think about how to do the antiderivative or the integral and kind of think about the meaning of that. Okay, so we've got a person that is driving a car along a straight highway. We have the clock start, and they are moving at 10 meters per second in the positive x direction and passing a signpost located at 50 meters. Okay, so we are given the initial position there. Okay, because at t equals 0, they're at x equals 50. They're not at x equals 0 at t equals 0. Okay, so this right here, this is our x naught. Okay, and this is a one-dimensional problem, so we don't have to worry about y. Their acceleration as a function of time, got it right there. Okay, 2 meters per second squared. Okay, so that's that would be actually the initial acceleration. This right here, we can actually think of this as a x naught, because at the other part here is time-dependent acceleration, and it's actually telling us that the acceleration is decreasing, right? So we can see that as time grows, acceleration decreases. It will, it starts at 2. It will be gradually decreasing from there, linearly decreasing because we've got t, not t squared or anything. And that's going to eventually cause the acceleration to be momentarily 0 and then actually start being a negative acceleration, which will oppose the initial velocity, which is in the positive x direction. So at first, the acceleration and the velocity are in the same direction, but eventually they won't be. Okay, and some other things to consider is that since, or at least one other thing, since the acceleration is linear, okay, right, like I said, t to the first power, that means that the velocity is going to be quadratic, and the position is going to be a third order polynomial. Okay, so let's take a look at part A that asks what is there, as in the people driving the car or the person driving the car, x velocity and position as a function of time. Okay. So we want the x velocity, so we want vx or v sub x as a function of t and x as a function of t. Okay, well, let's go ahead and integrate, right? So we know, okay, and we know by the definition of acceleration that it's dv dt, okay? So then we can rewrite this as a dt equals dv. Okay, so I just cross multiplied by dt, and then I'm just going to continue with this and integrate both sides. Okay, so here I'm going to integrate a dt. All right, and then here I'm going to integrate dv. Okay, and I'm obviously integrating across the differential, right? So here I'm integrating across time, right? So really like t1 to t2, and here would be v1 to v2 if it was a definite integral, right? And certainly I could set it up that way, but I don't want to here because I'm not interested in a particular time. I just want to know in general what the acceleration is doing. So I actually want to leave this as a, rather than definite, indefinite integral. Okay? So we'll go ahead and continue with this. Plug in our given function for acceleration, 2.0 meters per second squared minus 0.10 meters per second cubed t. All right, and then times dt, and then that's just going to equal dv. Okay. All right. Excellent. All right. Well, the integral of dv, I should say. Okay, let's do it. Let's integrate. All right, so then this here is going to be, when I take the antiderivative or the integral of this function for acceleration, I'm going to get 2.0 meters per second cubed times time, and then, second squared. Actually, that part shouldn't change. Times time. There we go. And then minus. And then we're going to be, let's see, because this is going to be 1/2, so I'll just put it in front. 1/2, 0.10, and then t and we'll leave the units here. I get every time. Meters per second cubed times t squared. Okay? And then plus some constant, which we'll call c, and then that's just going to equal v as a function of time. All right? Because basically here, right, our constant was, and by here I mean right here, our constant was 1, so when we take the antiderivative, it's just going to become v. Okay? All right. Okay, looks good. So the next step is to plug in our initial information to solve for c. Okay, so I'm just going to write here, and to find the constant of integration, c, we use t at, sorry, not t, well we do use t, but we use v at t equals 0. Okay, so we'll plug that in because we know that, right? And we know that at t equals 0, v is 10 meters per second. Okay? Okay, so let's plug that information in. We'll go ahead and put it on the left-hand side. So I'm just going to have 10 meters per second. Okay, and that was at t equals 0. So what does that look like? Well, that's just going to be 2.0 or 2.0 meters per second squared times 0 minus 1/2. And here I'll clean this up and write it as, rather than 1/2 times 0.1, we'll just write it as 0.05 meters per second cubed times 0 squared plus c. So then that tells us that c is going to be 10 meters per second. Okay? Everything looks good. Everything has the right units. It's a good thing to check that each of these terms have the units of velocity. And that's why I knew that I didn't want to write 2.0 meters per second cubed, because the integral doesn't change the units attached to the coefficient. And by the coefficient, I mean like the 2. Right? The 2 is the coefficient. Yeah, but sure enough, because the 2.0 meters per second squared times seconds, seconds cancel and we just get meters per second. And so then that's the units of velocity. All right. And the same thing for the second term, and then obviously the constant of integration is a velocity as well. All right, so now we have the full time-dependent velocity function, which I'll write right here. So this will be our first answer. V as a function of t is going to be 2.0 meters per second squared times time minus 0.05 meters per second cubed times t squared. And then I'm actually going to put the constant in front, so I'm going in ascending order. So let's put this right here, 10 meters per second, and then plus, and move our expression back over. There we go. All right, so that's our answer. Let's put a box around it. Okay, so you just want to do the same thing for position. Okay, so the position function, what is that going to look like? So, all right, well, we've got that the definition of velocity is dx over dt. So then that we can write that as v dt equals dx and integrate both sides. Okay. All right, and then we can, that's going to give us, so I should put this in the next line, that x as a function of t is going to be, okay, so the integral of 10 meters per second plus 2.0 meters per second squared times time minus 0.05 meters per second cubed times time squared, all with respect to dx. Okay, so let's do that next step. Actually follow the rules of antiderivatives for polynomials, and this will be 10 meters per second times t plus 20 meters, times 1/2 times 20, 1/2 times 20 meters per second squared times t squared minus 1/3 times 0.05 meters per second squared times t squared plus a constant of integration. Okay, and we can kind of use the same logic. I'll put it right over here. And since x equals 50 meters at t equals 0, we see c equals 50 meters, because we could just imagine plugging in 0 for each of the terms here that actually have a t, and those will all zero out. Well, that one is one term, and so that will just tell us that c equals 50. Okay. All right, put an arrow here. Okay, and then we can finally write the full expression for position, and I'll clean up the decimals. So 10 meters per second. Oh, let's put the 50 first. So 50, positive 50 meters, plus 10 meters per second times time, plus 10 meters per second squared times time squared. And then over here, let's actually see what we get for 0.05 divided by 3, which I don't know off the top of my head. All right, so let's do that. All right. Okay. Okay, there we go. Cool. My calculator simulator was off. Okay, so we'll go ahead and just take 0.05 divided by 3. Okay. All right. So 17 million, or 17 milli, right? So 17 thousandths. Okay. If we round. All right. So minus 0.017 meters per second squared. T. Oh, and that should be cubed. I messed that up here, because of course that happened when we did the antiderivative. D cubed. Okay. So that's our answer there. Okay. Great. Okay, so that's part A. So let's move on and look at what they're asking for part B. When is the car's x velocity greatest? Okay. Well, to find the maximum x velocity, we need only find the point where the acceleration is 0, because that's going to be a a maximum or minima of velocity. Okay, so let's take a look at that. And actually, what's not a bad idea at all is, let's go ahead and graph this to take a look at it so we can see our velocity. So we're going to have 10, and then, okay, so 10, and then plus 2 times x, okay, so there we go, and then minus 0.05, and then x, and then squared. Okay. Okay, so that will be our function. We're going to go ahead and graph this. Okay, so you see we have to do, let's take a look at our zoom here, or our window. So our zoom, we want zoom fit. Okay. Oh, so all right, so here we see the graph. I've adjusted the window here to go from -10 to 35 on the time axis, and -15 to +35 on the velocity axis. Obviously, anything before time equals 0, so anything from before this point, doesn't make sense, physical sense. But yeah, here we start with our 10 meters per second, our initial velocity, and it goes up, and then to see here, that's when it peaks out, because at that point the acceleration has already passed into having a negative acceleration. It's going to start actually slowing the car down, because in other words, the sign of the velocity and the acceleration will disagree. Okay. All right, so we can go ahead and take a look at that point, and that could give it to us, but we don't have to. In fact, to find that value, we need to only take the derivative of velocity here and set it equal to 0. And of course, the thing is that the derivative of velocity is acceleration, so we just have to find the point at which the acceleration is 0. So we just need to solve for time here by setting the acceleration equal to 0. Okay? Because the point at which the acceleration is 0, that's going to be the maximum velocity. Because at that point, after that point, the velocity is going to start to slow down. Okay? So I can write part B down here. Shouldn't take up a lot of space. Okay, so this will be part B. Okay. Velocity is maximum when dv dt equals 0. Okay, which is to say acceleration equals 0. So then we'll write that out. So we have 0 equals 2.0, and then meters per second squared minus 0.10 meters per second cubed times time. Okay, yeah, we're just solving for time. Okay, and so then we'll go ahead and do that. See, still see it. Okay, so then I'm going to subtract 2.0 from both sides and divide by 0.1. So then t is just going to equal negative 2.0 meters per second squared divided by negative 0.10 meters per second cubed, which will give us the units that we want, time. All right, so then that, well, obviously is just going to be 20. So 20 seconds is the answer. All right, and if we go over here and we move our point over to about where the maximum is, we should see that the maximum occurs, right? As we kind of move around, it's quite believable. We see that, yes, it occurs at 20 seconds. Okay, so let's move on to part C, the last part of this question, where it asks for the maximum x velocity and where's the car located when they reach that maximum velocity. Okay? So now they just want the value, right? Before was the time of the maximum x velocity. So, okay, we can easily find that. I'll speak about that in just a second. And then where's it located? Okay, so we're going to use the information we found, the time at which the maximum x velocity occurs, to find that we found that it occurred at 20 seconds. We're going to use that to answer both parts of question C. Okay, so I zoomed out so we can see what we're doing here and look at part C. All right, so part C, we want the first part. Let's see, what is the maximum x velocity? Okay, so v sub x is maximum at t equals 20 seconds. So v x max just equals v at 20 seconds, which is then just going to equal 10 meters per second plus 2.0 meters per second squared times 20 seconds. And then, all right, let me just resize this. Okay, and then we're going to have minus 0.05 meters per second cubed times 20 seconds squared. Okay, so what value will that give us? Well, we can see here, right, just graphically, we know it's going to be right around 29.97, right around 30, right? So let's go back. Okay, so we're just going to plug this in. 10 plus 20 multiplied by 20, so actually it's 20 squared, and then minus 0.005. All right, well, too many zeros. Okay, and then multiplied by 20 squared. Okay, looks good. Okay, so that's giving us 390. Perhaps I read the other one wrong. Okay, so 10 plus 20 times 20. That all looks good. Minus, okay. Okay, so the reason my number didn't make sense is I had 20 times 20, but it's 2 times 20. So I'll fix that right here. Okay, so sure enough, 30 meters per second is our maximum velocity. Okay, so real fast, last part here. Where is the car located when it reaches its maximum velocity? Well, that's simply a matter of then finding x at 20. So x at 20 seconds is just going to equal 50 meters plus 10 meters per second times 20 seconds plus 10 meters per second squared times 20 seconds squared minus 0.017 meters per second squared times 20 seconds cubed. Okay, so let's just get this value. So 50 plus 10 times 20. All right, and then plus 10. Okay, yep, 10 again. So I double check. 10 times 20 squared. Okay, and then minus. And to not round here, I'm going to do exactly 0.05 divided by 3. So, oops. Okay, 0.05 divided by 3, and then multiplied. Okay. And let's see here. Okay, so yeah, that should work out fine. Multiplied by 20 and then cubed. Okay, so let's make this 3. Get rid of the 1, so we're not raising it to 31st power. Okay. Let's insert here. All right, so I was getting numbers that were too big, 4,000 meters, 3,900 meters, and I realized it was because I'd made a mistake here with I wrote 10 instead of 1, because it was the 2 should have become the 1 when we did the antiderivative. 2 should become the 1. So I fixed that. So fix the correct position function and then plug that in. And I actually still have to fix it right here. All right. So when we do that on the calculator, we find that after 20 seconds, which is the time when the maximum velocity is achieved, the car is at a position of 517 meters. All right, so that's our final answers for part C. Okay, thank you.